IGCSE Computer Science Syllabus Statement 1.3.1e. Use logic building blocks to build other logic gates and circuits. So, this isn't part of, well, I mean, this statement isn't actually in the syllabus, but you still need to know about logic building blocks. And what we mean by that is using, like, multiple of a number of one logic gate to build other logic gates and circuits. So let's take a look at an example. So let's say we wanted to build the AND gate out of NOR gates. That's a good example. So what we do is put a NOR gate here, a NOR gate here, and a NOR gate here. Connect them. I should probably move that up a bit. Connect that there. Let me extend that, and then we have the AND gate, as you can see. And to prove that this is the AND gate, in case, I don't know, you don't know if this is the AND gate, let's take an actual AND gate, and I'll prove it. So 1, 0 makes 0, 1, 0 makes 0, 0, 1 makes 0, 0, 1 makes 0, 1, 1 makes 1, 1, 1 makes 1. So we've just built the AND gate out of NOR gates. So that's just an idea of how you could do that. So we did that out of NOR gates, but the most popular logic building block is actually the NAND gate. And as I've said in the past few videos, we were going to learn about the NAND gate and why it was so important. Well, this is it. This is the time where we know about it. Now, the NAND gate is really important and popular because, one, it's the cheapest gate you could buy, apparently, and two, you can build any other logic gate with just NAND gates. So let's take a look at that. We're going to build, in this video, every other logic gate with the NAND gate. So let's start with the easiest one, building a NAND gate out of NAND gates. So all we need is one NAND gate. Extend that there. And as you can see, a NAND gate is built out of NAND gates. To prove that a NAND gate is built out of NAND gates, we'll use a NAND gate here to show you that we can build a NAND gate out of NAND gates. So let's take a look at this. So, well, actually, yeah, 0 and 0 make 0. Oh, 0 and 0 make 1, and 0 and 0 make 1. That's the same. 1 and 0 make 1. 1. 0 and 1 make 1. 1 and 1 make 0. So that's proof that a NAND gate can be built with NAND gates. So let's try something a little bit different. So let's try creating a NOT gate, because a NOT gate is quite an important gate, as you can use the NOT gate to NOT any other gate. So let's try the NOT gate out of NAND gates. So what you need to know with this is basically the NAND gate can be treated as a NOT gate. And by that, I mean we can do something like, oh no, hang on, that doesn't look quite right. Alright. So as you can see, it NOTs the input. And to prove that, because I like proving things, let's put that there. You can extend that. So when this is 1, this is 0, this is 0, this is 1, and there. That's it. So I'm just going to get rid of all of this and all of this. So we can try building other gates with the NAND gate. So let's try building an AND gate with NAND gates. So we know that a NAND gate is basically an AND gate with a NOT put in front of it. So what we need to do to build an AND gate out of NAND gates is to put a NOT in front of it. So we just saw that a NAND gate can be used as a NOT gate. So all we have to do is this, and there is our AND gate with NAND gates. And to prove it, let's put an AND gate there again. As you can see, 0, 0 makes 0, 1, 0 makes 0, 0, 1 makes 0, but 1, 1 makes 1. So let's get rid of all of this, and then this. So let's try an OR gate out of NAND gates. So this is a little bit different in the way everything is placed. Sort of similar to our AND gate out of NOR gates. So we're making OR gates out of NAND gates, and it's basically the same positions, but we're using We're using NAND gates instead of NOR gates. So let's put a NAND gate there. We can extend that, and there is our OR gate, as you can see. And again, to prove the same here. So that's our OR gate out of NAND gates. Now let's create a NOR gate out of NAND gates simply by adding a NAND gate here. So this acts like a NOT gate. And to prove that, we can replace this with a NOR gate. So as you can see, it's the same as this is the same as this. Let's try something a little bit harder. Let's try the XOR gate. So we remember that the XOR gate looks like that. We put this here. The XOR gate is exclusive OR, so it'll only take one as only one as an input. Anything else, it will be 0. So this is how we do it. It's a little bit trickier. So I'm actually not sure if the course expects you to know this for the XOR gate, but we're going to do it anyway, just to be sure. So what we need to do is add another NAND gate here, add another NAND gate here, another NAND gate here, and a final NAND gate here. And what we're going to do is move this in a bit to give us some space. So there we are. So it's a little bit different how we connect them. So we put that there, and then we put this here, and put these here like that. And once we've done that, we just put this here and put this. Ooh, this is a bit weird. What I'm going to do is move this up like here, so it looks a bit better. And then we extend that to the output, and we can test both of these. As you can see, that works. So our final gate, of course, is the XNOR gate. So basically the XOR with a NOT in front of it. So just to remind ourselves what that looks like, the output will be 0 if only one input is 1. So it's basically a NOT of XOR. In fact, yeah, it is the NOT of XOR. So what we do, same principle again. We add another NAND gate here, and acts like a NOT gate, and then reset it. It's 1, 0, 0, 1. And that's pretty much it for the logic topic. The next topic is computer architecture, which is, again, more about hardware. we actually move on to software quite a bit later, after I think after storage, I believe, and then we move on to like operating systems or something like that, and then languages and some other stuff. So yeah, stay tuned, and yeah.